All right. Hello, everybody. My name is Attila, and I will be talking to you about my various war stories, experiences, etc. at the time that back in the day when I worked at Twitter. I was part of Twitter's runtime systems back in the day, runtime systems group, and we were in charge of just basically making sure that all the JVMs at Twitter run without hiccups. In the course, I did learn quite a lot about tuning JVMs for performance. I usually say that I learned quite more than I actually ever wanted to. And there's been some hard-won lessons. Typically, what happens is you have your developers who write their code, and when they are complete, they put it in production. Well, they don't put it in production. They start running it, and typically they figure out that, oh my God, performance characteristics of this thing are not nearly as nice as we would want them to, and that was when us came into play. That was when they would come to us, and then we would sit down and try to make sure that their stuff actually performs. We used to internally joke that there is this period between when developers finish the code and when it's production ready, and that was basically us. I don't work for Twitter anymore, so this has been some years ago. In the meantime, I spent more than 2 years at Twitter, mostly in the JVM trenches. I also optimized the garbage collector of the Ruby runtime as well. After that, I left for Oracle, where I worked on Nashorn, which is the JavaScript runtime on the JVM. I spoke about it last year. And as life has it, I'm actually not with Oracle anymore either. I circled back almost to Twitter. I'm now with this little startup called FaunaDB, which is mostly founded by some ex-Twitter colleagues. So it's a small company. About half of us are ex-Twitter employees, and we are working on creating the operational database to end all operational databases. You'll hear about us in due time, I guess. So with that, Twitter's and in general any web service's biggest enemy is nothing else than latency. People don't like slow websites. They will navigate the way they want to use it. It will feel sluggish. And it manifests itself at render time in the browser, manifests itself at network connections, manifests itself all the way to your server's latency. And there are separate groups that deal with how can you minimize the network latency, how can you speed up the rendering on the web browser, and so on and so on. That's not my table. I deal with server side. Normally, by far the biggest latency contributor on a service that's based on the JVM, and Twitter was typically like that. There was some Ruby, but it was being phased out mostly for Scala and Java-based services over time. By far the biggest contributor to latency is the garbage collector. Therefore, memory tuning is crucial if you want to have responsive applications. Aside from that, you can have in-process locking, thread scheduling, I/O, application algorithmic inefficiencies. We won't talk about those because they are not domain of tuning. Application inefficiencies can be solved by optimizations. I/O is different. I will talk a little bit about locking and thread scheduling maybe. As far as memory tuning itself goes, you can tune for different goals and you can have different approaches to it. Typically, you can tune for your overall memory size. You can tune for your oh, sorry, we're not there yet. Anyway, let's skip the slide mentally. I was talking about this. So you can tune for your memory footprint, you can tune for your application rate, you can tune for the amount of garbage collection that your system is doing. And I skipped slide back. When you're talking about tuning, you can tune all of these, but we will concentrate on memory, maybe a little bit lock contention. I have it in a talk. We'll see how we fare with time. As far as you want to tune your memory footprint, well, why would you want to tune your memory footprint? Well, the less memory your service needs, the less pressure there will be normally on the garbage collection. So the fastest garbage collection is the garbage collection that doesn't need to happen, right? So tuning for memory footprint is worthwhile as long as it doesn't conflict with your other goals. Sometimes it does. We'll get to that. A very blatant sign that your application is using too much memory is obviously if you're getting an out-of-memory error. I know it sounds silly and very obvious, right? It's also one of those things that you don't want in production. So you would be surprised how often it does happen. The reasons why you might get an out-of-memory error, or maybe you're not getting an out-of-memory error, but your application is dock slow because it just doesn't have an in-memory, free memory overhead to work with. You might just have too much data, quite obviously. Your data representation might be inefficient. Back when I used to work at Twitter, I would typically use the word fat to refer to inefficient memory representation. It's a great way to evoke your mom jokes, which is also, I mean, it's a great thing when you work in a company that's mostly populated by 20-somethings. You can also have a genuine memory leak, but we won't discuss memory leaks. A memory leak is an application bug, so that's something that you need to track down and fix. So, how much memory does your application actually use? There's a really easy way to figure that out. I will have various GC flags interspersed in this talk at times. I also can't use this LED pointer because it's also a LED screen, so I will just point. So if you run with verbose GC, you will get nice log output, and you can observe your numbers in full GC messages. Typically, it looks something like this. It will tell you when a full GC occurs, this much memory was used, and after the GC happened, this much memory is used now, and this is the total allocated by the JVM. The JVM typically allocates more than what's used and doesn't release back to the operating system immediately, because if it did that, it would have to reallocate release on every GC cycle, and that's plain inefficient. So once it allocates additional memory, it tends to keep it. Sometimes it does release it. I'll show you how it does that. What you want to is, you're interested in this number, right? This is your live set. After GC, this amount that remains here is the live set of your program. And if it's a lot, specifically, it's very close to either this number or it's very close to the physical capacity of your machine, then the obvious question is, can you give the JVM more memory? More is always better. As you know, performance problems are resource problems, right? Most performance problems, even throughput and latency ones, can quite often be fixed by throwing more memory at it. And if the answer is yes, I can give my JVM more memory, that's great. Give it more memory. Fucking hell. All right. For the record, this stand doesn't have a lip, so this could happen. I'll just put this poor guy here and hope that it lasts until the end of the presentation. Oh, we lost the screen. Cool, we're in business. If this isn't an advertisement for Apple hardware, I don't know what is. All right, so the other question is, do you need all that data in your memory? Maybe you don't. There are techniques for making sure that you don't keep everything in memory. You can use LRU caches, or you can use soft references. There is an asterisk here. I should probably make it bigger, and I will talk about it. When I joined Twitter, I thought that soft references are great. And since then, I have, both at Twitter and at Oracle, encountered a situation where soft references bit me really hard. So basically what happens here is if you have data that can be recomputed, reloaded from external sources, right, then you don't need to keep it in memory all the time. Even if you loaded something in memory, you don't necessarily have to strongly reference it all the time. Sometimes it makes sense, if it's cheap to reload or recompute, to just keep some of them in a least recently used cache and make sure that it's expired. So you can manage your memory usage like that. So fat data is normally not an issue. These days you just structure your classes, subclasses, objects have pointers to other objects and so on. Most of the time it's all good. Just, keep to your nice object-oriented principles, structure your code as you would normally. But again, when you work at places like Twitter, things come like the research team comes around and they tell you, hey, we need to load the full Twitter social graph in a single JVM. We've been giving this guy 60 gigs of RAM and it still doesn't fit. Yep. Or load all user metadata in a single JVM. So at this point, actually thinking about how can you make your internal data representation objects smaller, it works at these economies of scale, right? So when back in the day, I don't remember, but this was probably several tens of millions of graphs, and even if you don't do the full social graph, just do it for active users, you will still end up with a lot. And there's always problems like that. So normally, and this is all specific to the hotspot JVM. On hotspot, whenever you allocate an object, it will have a header, and that's 2 machine words. A machine word is whatever is the native size of the word on the machine. These days it's 64 bits. So whenever you allocate an object, that's at least 16 bytes. If you want to make it sound scary, you can say 128 bits. That's a lot, right? So you just do a new Java-lang object. That will take 16 bytes. One word is the class pointer. The other word is typically used for locking and some other purposes. Like if you take system identity hash code, then it needs to be permanent, then it's stored there, etc. If you allocate an array, it's even worse. The smallest array you can allocate is a zero-length array of bytes. That thing will still cost you 24 bytes because you have it's an object, right? So you have 16 bytes for the header, you have 4 bytes for the length of the array, and since we are on a 64-bit architecture, you have 4 bytes of padding until the next multiple of 8. So if you padding for subclasses. If you have this simple class that only has 1 byte field, smallest thing you can have, this costs 24 bytes because you have 16 bytes for the object header, you have 1 byte for that field, and then you have 7 bytes of padding until your next multiple of 8. If you subclass this guy, you would think, oh, there's plenty of space in that padding, so this should still fit in 24, right? Because 16 for the header, 1 byte for X, 1 byte for Y, 6 bytes of padding. Nope. Thing is, padding happens on a subclass by subclass level, so the in-memory layout of this class will be 16 bytes for the header, 1 byte for field X, 7 bytes padding, 1 byte for Y, 7 bytes padding. So if you're conscious about memory, I guess go easy on subclasses. This is a terrible advice to make. I mean, quite often, whenever you are talking about performance, sooner or later you will find yourself at odds with nice design. So I would say keep subclassing, keep those abstraction hierarchies nice if you can. But if you find yourself in a situation that is biting you performance-wise, then consider flattening it. Of course, if you have a class that has a reference to another object, doing something like this will immediately take away 40 bytes because you will have one object of C and another object that's 16, and this one is 24 because it's header plus 8 bytes for a pointer. And similarly, array elements, there's no such thing as inline array elements. There's no such thing as structs in Java yet. There's this project Valhalla, which is adding value types to Java, and it will be a huge boon once it's shipped. I'm not sure when does it ship. Probably not Java 9. No, certainly not Java 9. So, with Java 10, I guess, we will hopefully have actual value types in Java. So you could have a situation where this object is actually embedded, well, not as an object, but as a struct in another. So C programming language style structs are coming to the JVM, but until they are here, we'll have to cope. You can take slimming to the extreme. So remember that full follower graph in memory research project that I was referring to? We ended up there representing each vertex, which is a user, edges, as int arrays, because we just couldn't afford the pointers at that point. It was that big. If it grew even larger, I even suggested to them that, you're just linearly scanning these arrays. We could do some variable length differential encoding in byte arrays. So if you have objects and you need to represent like huge number of connections, say, all people following Justin Bieber is a typical example, right? But, and I actually suggested this sort of like a joke, but them being data scientists, they immediately liked the idea. Anyway, as I say, don't do this at home. This is something that you really need to resort to when things are going bad. There is such a thing as a compressed object pointers, which the JVMs typically use. The idea is that since we are padding every address to a multiple of 8, the least 3 bits of every pointer are 0 anyway. So why not just right-shift them by 3 and use 32 bits? So with 32 bits, you normally can address 4 gigs of memory, but if you treat every value as being divided by 8, now suddenly you can address 32 gigs of memory. So the JVM actually does this quite nicely. For some reason, if you set your heap to 32 gigs, it will not use compressed pointers, but it still could. Automatically, it uses it until about like 30 gigs. And if you need more than 32 gigs of heap, then you must use uncompressed pointers, because with compressed pointers, the max you can address is 32 gigs. This also means that there actually exists this uncanny performance valley that you can't do much about. So there was an Oracle study on very large corpus of JVMs that said compressed pointers reduce the memory load by anything between 25 to 33%. It obviously depends on the mixture of objects in your running JVM, how many pointers do you have. But this also means that if you need more than 32 gigs of RAM, if you go to 33, suddenly, because your pointers have now inflated, your JVM will be able to store much less objects in memory. So if you need to go above 32, you need to go to at least like 42 to 48 to actually get the same amount of data that you can store in memory, same amount of objects that you can store in memory. So between 32 and 48, you don't gain anything. You actually lose because of the pointer inflation. So take care of that. If you see that you need more than 32 gigs of RAM, don't go to 36, because you will actually end up being worse. There's just a handy chart showing that, how do the various sizes look in uncompressed and compressed pointers. Also 32-bit JVMs, but nobody uses those anymore. There's some other things that you can figure out, and this is old, but it applies. So avoid using instances of primitive wrappers. This is such a obvious and blatant thing that I'm even ashamed of pointing it out, but sometimes you don't figure it out. So when I joined Twitter in 2010, and this is like dating it, we still use like Scala 2.77, and it turned out like a sequence of ints will use boxed integers, and an array of int will actually store primitives. Now the first one needs this many bytes. Notice this very large factor here. And the second one obviously needs much less. And you don't really notice this except when you look at your program with a profiler and you see, my God, where do all these boxed integers come from? Then you start digging and then you figure it out eventually. This was fixed in Scala 2.8, but that's not the moral of the story. I could have used any library for illustration of the concept. The moral of the story is that you don't know the performance characteristics of your libraries. The only way to figure out the performance characteristics of the libraries is to run an application under a profiler. If you want to optimize and tune JVM, you will need to familiarize yourself with the profilers. There's really no way around it. Either that, or read and understand the source code of every library that you rely on. Your pick. For me personally, I would be too dumb to understand all the libraries that I rely on, so for me, using a profiler seems like a easier way around that. Speaking of libraries, there was also this funny thing with the map footprints. We used to use Google Guava, and it's a great library. And it has this innocuously looking, very default, right? Map maker, make map. What can be easier than that? And it turns out this will create a map that eats more than 2 kilobytes of RAM. Again, not a big deal unless you have a problem where you need to create several millions of them in memory. So, and obviously we had that. So. And what you can do, this creates concurrent maps. So one funny hack I did in one particular problem is I reduced the concurrency level to 1 to make the map. And now it suddenly just took 352 bytes, and we could store about 8 times as many in memory immediately. And it was great. Now, what's the difference here? The concurrent maps are typically implemented by striping. So, striping to the number of concurrent, usually CPUs or cores on your machine. So this can end up having 16 different stripes to increase the concurrency on reads and writes. And if you tell it concurrency level of 1, you just have 1 stripe. Okay, but why is it concurrent then, right? What sense does this make? Actually, it makes a lot of sense because you still get concurrent reads. So, I mean, compare this with a synchronized map. Synchronized map, still, you can only have 1 reader or 1 writer in it. Concurrent map with concurrency level of 1 can still have multiple readers, but it can only have 1 writer. And the writer will also lock out the readers, but still better performance. And it's also not sensitive to concurrent modification, because the others might throw a concurrent modification exception. This doesn't. So we again had this thing, a service where you fan out tweets. So Twitter, even back then, was mostly using a push model. So somebody tweets, and somewhere needs to be a machine that has all of the followers of that person in a map and pushes it out to all connected clients. And again, if you have a very popular person that tweets something, then somewhere you will have a large map. And most of those maps are actually really small, but you also need to have a lot of them in memory. All right, looks good. Yep, okay. So another thing I found is, and again, just as previously my point was not about Scala, what I'm telling you now is not about Thrift. Thrift is a wire format that was developed by Facebook and that Twitter is internally using a lot. It's so, you know, a bunch of microservices, they need to send data to each other, and Twitter's chosen wire format was Thrift. Thrift is pretty great because, well, the things that I love about Thrift are also the things that I hate about Thrift. Thrift is using wire format that has no description in it. It's very compact. But it also means that you need generated code that can read it from the wire, because it has no self-description. You always need to have coding and decoding classes for it. And problem is, some people were using them as domain objects, which is really dumb. So here's what happens. You have an object that's named, say, you have a class, person, right? And you have a Thrift via format, and your Thrift code generator generates you a person class. It has a string first name, string last name, whatever date of birth, and so on. It looks great. It's just exactly what I need. I'll just use this. No, you don't want to. And here's why. Every Thrift class that has a primitive field will also have a bit set. It has a bit set because Thrift is really thrifty on the wire. So if you say have a Boolean field that you never set to anything, it will remember in this bit set that I never set it, and it will not send it over the wire. Now, just having this innocuous bit set will add like 72 bytes of overhead to your object. Here's why. You have your Thrift generated class, 16 bytes at least. There's a pointer, 8 bytes. There's a bit set, 16 for the header, another pointer to the words, another 8 bytes, 4 bytes for the words in use. There's an actual long array here, which is another 24 bytes for an array, and then you have like a single long element here, which is 64 bits. Oh yeah, that's the 1 bit that you actually use. So, and you know what? This is actually great. If you have a data transfer object, you don't care about this because it only lives during the time of a request response cycle, and then it's thrown away and garbage collected. But we also had some people at the company that just kept those things in memory. So they were like, I'll just keep a Thrift proxy and whatever data I deserialized, I'll just keep all of this in memory. And then you got stuck with your 72 bytes of overhead. And then of course they come to you and they tell you, well, I have this 64-bit JVM, 64 gig JVM, and my data doesn't fit in. Java sucks. So yeah. And what I did, yep, screen is dead again. So anyway, what I did here was I went in, refactored the code, like you had opportunities for various optimizations. We had a class for location, which had like a city, region, country code, metropolitan area, latitude, longitude, and so on for like Twitter's geolocation stuff. And then they just auto-generated it from Thrift. And so it had so many opportunities for optimization, right? Actually, you can look at the side screen. Side screens still work. And so this was what Thrift generated. And when you want to send a location over the wire, this is fine. But if you want it in memory, you can like extract this separately, only have this here. It has a pointer shared location, so these are already much smaller. Country codes can be interned. And you know, cities typically belong to a single country at a time, except in unfortunate circumstances. And so on. And you know, suddenly like 60 gigs of RAM went down to 20, and you know, Java doesn't suck anymore. Yep. As I said, it's not about Thrift. Thread locals, you know what, I'll skip this. Let's talk about fighting latency. So what I was telling you about until now is various techniques for restructuring your program, but let's look into like actual latency fighting. If you were studying computer science at the university, you probably were faced with this thing where they typically tell you there's a trade-off between memory and time. Yes, there is. And this is true, it's also overly simplified. I typically think about this as a triangle, very novel, right? Because you still have the memory, but time is a concept that can split into either latency or throughput. Now, what you typically want you want to increase this guy, you want to decrease this guy, you want to decrease this guy. Also, it's mentally a little bit confusing when you need to think about, I want to increase one, decrease the other. So that's why I kind of invented for my own internal use. Instead of memory usage, I figured out compactness, which is higher the less memory you use. And instead of latency, we use responsiveness, which is the higher the less the latency is. And so what happens is that for any given combination of hardware, operating system, and your application, you will actually have some fixed constant, which is some kind of a weighted multiple of these three. And when you are tuning, you have a fixed A. And you are trying to increase one of these while decreasing usually the other two. You can also optimize your code or optimize your system, which is a means of increasing the overall product. You can optimize your code by fixing algorithm inefficiencies, throwing more hardware at it, switching to a better operating system, and so on. But that's not tuning. That's the difference between tuning and optimization. Yeah. Normally, responsiveness and throughput are at odds with each other. This is an imaginary time diagram of an application that's responding to requests over time. And if you optimize for throughput, you can see these guys are more densely packed, so you process more of them, but every now and then one of these will suffer a catastrophic GC pause, at which time it will wait until it goes further. If you optimize for latency, you typically end up with smaller throughput, and each of these will incur its own little overhead. Sometimes you have bulk applications and you want to go with this, but this is actually more preferable, especially for web applications. It's easier to plan for this. If you throw more hardware at a system, then you know that this will go lower. If you throw more hardware at a system that's throughput-oriented, there's not really telling what will happen. I mean, it should buy you more throughput, but it's not as clear-cut. Biggest threat to responsiveness in the JVM is the garbage collector. And here's how typically the memory layout in a JVM hotspot looks like. You have your heap, which is split into new part, which is Eden and Survivor, and the old part. You also have some other things like permanent generation, which went away with Java 8, and code cache. We are not talking about those at all. So, how does young generation work? Every new allocation happens in the Eden. It's super cheap because there's a pointer that starts here, and you allocate an object, and you allocate an object, and you allocate an object, so it's always just a pointer increment. It's really fast. And when Eden fills up, that's where a stop-the-world copy collection happens. So all the live objects are traversed from GC roots, which is everything on stack, everything is CPU registers, and so on, and gets copied in, for sake of argument, survivor space 1. And at that point, this pointer is just reset to 0, and everything starts again. When it fills up again, then it again is collected plus the survivor space 1, and everything that survived is copied into survivor space 2. So survivor space 1 is always empty, another is full. And eventually, things from survivor space go into the old generation. Now, what's important to note here is your dead objects are free to collect. That's why allocating is not a big deal in Java. Well, you pay the constructor price, but other than that, if the objects die, they are not even traversed here. Only the live objects are ever collected from the Eden and put in the survivor space. And then the pointer is reset. So the dead objects are summarily thrown away. After several collections, your survivors get tenured into the OGen. So your young generation operation, young generation size should be big enough to hold more than one set of all your concurrent request response cycle objects. So if you have an HTTP server, you have 50 threads, let's suppose, and each of them needs about 10 megs of RAM to process a request, then you will need at least 500 megs of young size. That's actually ridiculously low, but just for the sake of argument. So that all the garbage it created can, in at least one request response cycle concurrently can fit in it. And your survivor spaces should be big enough to hold active request objects plus those that are tenuring. So actives, maybe your HTTP request is in progress. It generated 4 megs of garbage. It will generate another 6 megs of garbage, but at the point it has 1 meg of live objects. So it should fit in there. You have several collectors in the JVM. You have throughput-oriented ones, and you have low-pos ones. Low-pos ones, the concurrent mark and sweep is a good choice for Java 7, Java 8 as well, although it now use G1 GC by default. I cannot really talk about it because I don't know much about it. And so what's really great is that if you use the throughput collectors, those guys can actually automatically tune themselves. You can tell them things like, this is the maximum GC pause that I want. This is a throughput goal. And this is the ratio of time, like 1 to 19, that I want to spend in GC. And they will try to size the memory region so they actually meet this goal. Memory tuning is typically like rings of hell. There's many of them, and you don't want to go too deep. This is the first ring. If you can manage it here, that's great. Try the adaptive sizing. One place where you really want this is one of the Twitter's queuing systems, internal queuing systems with adaptive sizing policy. You can see it's pretty low, and then a lot of load gets thrown at it, and the adaptive sizing policy increases the memory size, increases it even more with another peak, but then it comes down. The ideal operation of a queue is being empty, right? Message comes in, message goes out, message comes in, message goes out. You want them to go, but sometimes by the nature of it, they will pile up. And that's when you need to adapt. So for queuing system, throughput policy is pretty great. So if you have any kind of bulk service, use throughput collector with no adaptive sizing. For everything else, throughput collectors are good, with adaptive sizing policy are a good first try. And if it doesn't work, then you need to use concurrent mark and sweep. Anything, whatever you do, you need to first tune your young generation. That's crucial. If you enable those flags, you will see a lot of interesting info in the logs. You need to determine your desired survivor size. There's no such thing as a desired Eden size. The more memory you can throw into Eden, the better. There are some responsiveness caveats with that, but this is general advice. And basically, the survivor size, after every every young gen GC, minor GC, you will see that the Eden space is 0 because we just collected it. It's always 0. It's the most useless piece of information ever. One survivor space is always empty, and another will hold some number of objects. What's the ideal value here? Anything below 100. Because if this goes to 100, it means that not all of your surviving new objects can fit into a survivor space. They need to go somewhere. So where do they go? They get forcibly tenured into the old generation. And you want to, ideally, not go into the old generation. So there's also this interesting thing that shows you how many generations did objects survive in a survivor space. You want this number to be decaying, like really decaying. If it's not strongly decaying, then your memory load is increasing. That means two things. A, your application is starting up and it's creating all the objects, buffers, etc. Or B, you have a memory leak. So if this is pretty constant, then you have a problem. Tuning the CMS is, again, give your app as much memory as possible. The thing with CMS, it's concurrent mark and sweep. It's speculative. What CMS does is your application is running and it's allocating memory, and CMS runs concurrently, right? It's a concurrent mark and sweep. It runs as your program is running, and ideally, it can clean up memory faster than your application allocates it. As long as it happens, you're fine. Again, just try using CMS without tuning. Just use verbose GC, print GC details, see whether you observe any full GC messages. You don't, you're done. Don't go to the next ring of hell. If you do, then go back, tune the young generation, then come back. And tuning the CMS old generation, you need to keep the fragmentation low. CMS does not compact. That's one of the things that it doesn't do normally. And you need to avoid full GC stops. Normally, computer science, when you have two goals, they're always in conflict with each other. This is probably the only time in my profession when I figured that there is a goal that I have two goals that don't conflict with each other. It was wonderful. And what you need to do for CMS, you need to find your minimum and maximum working set sizes. There's a trick to doing that. You switch to a throughput collector, which only collects when the memory fills up. You see how much did it clean, so you will observe an actual maximum working set there. And then over-provision this number by 25 to 33%. So you see that your application in stable state is always using 10 gigs of RAM. Well, give it 13 or 15 or more, as much as you can. Because, as I said, the CMS needs space. because as it's cleaning, your application is still allocating. So you want to have extra free space for your application to be able to allocate while CMS is trying to catch up. People will usually say, well, that memory is just sitting around doing nothing. Well, it's not doing nothing, it's a safety cushion. Because if your application outruns the CMS, allocates all the memory, you know what happens? A stop the world full GC happens. And since the CMS does not compact normally, this is when it will compact. And that's when you have like 2-minute pauses on large heap. In a distributed system, a 2-minute pause is indistinguishable from a host that went down. It's that simple. So you can also do things. CMS doesn't run all the time. When like 80 to 75% of the memory is allocated, that's when it kicks in. It tries to save CPU. And there's actually a flag for that. And you can actually lower that. If you have spare CPU, you can even like lower it to 0. This means that basically CMS will just run in a cycle all the time in the background in your application. If you have spare CPU cycles, that's a good thing. Usually you have. Most applications these days are I/O bound, so you will typically have spare CPU cycles. All right. And you know, if your responsiveness is still not good enough, then, well, this is pretty much almost the last slide. If you have too many live objects during young Gen GC, you can try reducing new size. This is weird. This is a weird thing that sometimes happens. At Twitter, we had a situation where collecting the young generation was taking long, but that was because we had a lot of new objects that were surviving. In that case, you actually reduce the new size. You even reduce the survivor spaces. So contrary to conventional wisdom, you want those to like tenure into old generation where CMS can hopefully better handle them. And, you know, it does work, but it's weird. It always depends. I mean, again, you need to profile, you need to watch it. And finally, if you can have too many threads. We had a service that had like thousands of threads. Threads needs to be scanned for GC because they are live routes. So you either need to find the minimal concurrency level that works for you. If everything else breaks, you need to break your service into several JVMs. That's the ultimate performance tuning advice. Use more processes, potentially more boxes. But that's literally thinking outside of the box. And I think we are at time. Is that right? Okay, that's great. Because I would have had a small like part 3, but that would have been another 3 slides with unrelated advice. And I think that at this point, this talk is pretty round as it is. So thank you for your attention. All right. Am I taking questions?
Thank you for your speech. Can you please tell me, have you used off-heap storage for your purposes? It seems like it's a valid proposition to use off-storage heap.
Okay, so the question is, have we used off-heap storage for our purposes? Yes, we did. Actually, while I was at Twitter, we had a service that was adopting Cassandra, and we had some Cassandra committers being employees at Twitter at the time, and they were tuning it a lot. And they were experimenting with off-heap buffers. They work, but the important thing to realize is that all you can store is raw bytes. So you will need to take care about encoding and decoding things in your byte buffers. And you also don't get any benefits of garbage collection. You need to manage those buffers on your own. In Cassandra's case, this was workable because they were using those byte buffers as serialization buffers before flushing to disk. So there was a linearity to it. So you would linearly fill up a buffer, and when you flushed it out, it was clean. But we also had some people experiment with off-heap storage for their own byte-encoded stuff. That's when they couldn't make the JVM perform as well as they wanted to. And that was horrible because they ended up writing their own free lists in the byte buffers and so on. So yes, you can use off-heap storage, but be wise about it. If you have a really good like boundaries of liveness, and preferably those are linear, then it's actually a pretty good proposition. But again, you will have to go back to raw byte arrays and encoding your data over bytes. So it's not terribly object-oriented.
Thank you for your talk. From your experience in your career, what was the most craziest reason of out-of-memory error?
What's the craziest out-of-memory error? Well, before Java 8, you have permanent generation in JVMs. And it can throw an out-of-memory error as well. But what's funny about it is that things that are kept in a permanent generation are class data. And I had a system where a lot of classes were loaded on the fly. So it was actually something like OSGI, so a versioning, something that could load different versions of the code. So what happened was that even though we were keeping the classes in ordinary heap, the class objects themselves, held by soft references so that the GC can clean them out whenever it needs them, the regular heap never filled up, so they were never cleaned. The permanent generation, on the other hand, it filled up. So we had this situation where we were getting out-of-memory errors in the permanent generation while we still had a plenty of heap, and the idea was that we are softly referencing those class loaders. They will get garbage collected when they need to get garbage collected, except they weren't, because the garbage collection of cleaning of soft references was governed by the ordinary heap, and instead we had a out-of-memory error in the permanent generation. This took a while to figure out and track down because it was out-of-memory error, but we have plenty of memory. What's going on? Yeah, I think that was the craziest out-of-memory error that I ever had. It was even pre-Twitter. All right, any more questions? Okay. Oh, there's a question.
Thank you for speech. I have one question regarding to old generation and new generation. You told that we should, for sometimes we could pass all our object to old generation, and because we have GC and multiple reducing the memory, it's a good idea to pass all object to old generation, or it's better to avoid this situation?
Normally, okay, so the question is it a good idea to like force objects, if I understand correctly? The idea is it a good idea to force objects into the old generation? Normally, no. That's because most objects die young. That's the so-called young generation hypothesis, and it's been observed that for majority of the programs out there, all the objects that you create, they will die while in the young generation. You don't really want to, so ideally you want to actually you want them to die while they are young, and only few should tenure. So ideally in your old generation, you only have objects that are the infrastructure of your program, but anything that's transient data, request response cycles and so on, that should ideally all just, you know, live and die young. When I was telling you this, is that if for some reason your objects are not dying young, I'm not sure why, so your application logic is such that your objects are not dying young, then it makes sense to make the young generation small and shove them off, because even if you have concurrent mark and sweep, the concurrent mark and sweep only works on the old generation. New generation is always stop the world copy collected. And it's faster the less objects there are. But if most of those guys in Eden survive, then it can be slow. So in that case, you might be better off just having a small new size, making sure everything tenures, and then let CMS take care of it. But that's unusual, that's an anomaly. If you profile your application, you notice this trend, then it makes sense. But this is like counter to the normal advice, which is give as much memory as you can to the new generation, because the more memory you give to the new generation, the higher the likelihood that objects will die young, because the bigger the new generation, the definition of young becomes also larger, right? So they will be young longer. So as I said, this only happens if your latency problem is due to the minor GC collections in the new generation. We did have that. So we had an application that was tuned to the bone, and still we had some undesired latency, and it turned out that all the latency that remained was new generation collection latency, and we had to do something about it. So this is counterintuitive. As I said, rings of hell, we were pretty much near the bottom here. Okay. All right, any more questions? All right, I think we're done then. Thank you again for